Grade 12 Physics, Energy and Momentum, Note number 11, Gravitational Potential Energy. So in this note, we're actually going to look at a grander form of the equation for gravitational potential energy. Earlier in the unit, we just used the equation E equals mgh. But really, that's just a simplified equation of what we're going to look at here. So this is very close to Newton's universal law of gravitation equation, but this is now for an energy. So really, gravitational energy, Eg, is equal to the negative of big G times the mass 1 times mass 2 divided by a separation distance. So this is E is energy in in joules. G is a universal gravitational constant, so it's a constant value, 6.67 times 10 to the negative 11 joule meters per kilogram squared. The masses are masses in kilogram, and R is the separation distance of the two objects in meters. So when do we use this? We use it for when we're far away from Earth, so when we have these humongous distances where the force of gravity starts to get weaker, where we're not exactly at 9.8 anymore. And we can use it for gravitational potential energy between two arbitrary objects, where one of them doesn't necessarily have to be Earth. But why is it negative? There is a negative in front. If we think of E equals mgh, as h increases, so does energy. So that means as we get higher and higher and higher, gravitational energy gets higher and higher and higher. But this one, if we look at the equation, if R on the bottom were to get bigger and bigger and bigger, gravitational potential energy would get smaller and smaller and smaller. So that's a bit of a dilemma. So what we do is if we place a negative in front, as R goes up, here the energy will also increase as well. So as R increases, E grows from negative infinity to 0. So this is a way we can get around, we can still say that energy is increasing as our separation distance gets larger. So what we're going to do now, let's use this new formula in an example. Let's say we have two watermelons separated by some distance, and we're going to find the gravitational potential energy between those two watermelons. So each of the watermelons are going to be 1.25 kilograms. Separation distance is going to be 0.45 meters. All we're really going to do is we're going to plug all of these numbers into the equation and see what the answer is. So Newton's universal gravitational constant, 1.25 times 1.25 divided by the separation, we get a value of 2.32 times 10 to the negative 10 joules. So not a lot of value, not a lot of gravitational potential energy between them, but we wouldn't expect that anyway. We can use it to do a derivation for something called escape velocity. Escape velocity is basically the velocity needed to escape the gravitational pull of a planet. So here we're going to do a little bit of a thought experiment. What velocity is needed to fully escape the gravitational pull of Earth? So let's say we have these following conditions. Here's the planet Earth. We're going to start on the surface. How fast do I need to throw a baseball straight up to fully escape Earth's gravitational pull? Well, you might ask, like, how far? How far do you have to go to escape the pull? It turns out you have to go an infinite distance to fully get away from Earth's gravity. So let's use E equals E prime to find out how fast I have to throw this baseball. So there's gravitational potential energy plus that kinetic energy that I'm going to throw the ball with equals Eg plus Ek prime. When I get to infinity, it's going to go to a stop, so I'm going to have no kinetic energy at the end. And if I'm at infinity, Eg is going to be 0, because if you divide by infinity, that makes a fraction go to 0 as well. We're going to put in our expressions for Eg and Ek. One of the masses will cancel out. The other mass left over is going to be the mass of the planet. So if I rearrange for V, V is our escape velocity. This is what the equation turns out to be. The escape velocity is the root of 2g times the mass of the planet divided by your separation to the middle of the planet. So let's use it here in an example. Let's find the escape velocity, what the actual value is on Earth's surface. So again, this is like I'm standing on Earth's surface. How fast would I have to throw a baseball to get it to fully leave Earth's gravitational pull? So here we need the mass of Earth, which is 5.98 times 10 to the 24 kilograms. We also need the radius of Earth, that would be my separation between me and the center, and that's 6.38 times 10 to the 6 meters. We're going to put those numbers in the escape velocity equation. So 2 times g times the mass of the planet divided by the separation between you and the core. It turns out you need 11.2 kilometers per second to throw that baseball in order to get it to infinity. Anything faster than that would also work, but 11.2 would be the minimum. Now what about from the height of the space station, which is about 450 kilometers and up? The expectation would be as you get further away from a planet, gravity gets a bit weaker, so we should find a value here that's a little bit less. So we put our numbers in. In the separation distance r, we're going to have that radius of the planet plus this new height, and we find here it's 10.8 kilometers per second, which indeed is less than 11.2.